Hi everyone! Today let's talk about session 13.4 and 13.5, triple integrals. Integrating a three-variable functions f of x, y, z over a three-dimensional solid region in space is done using a triple integral. Evaluating a given triple integral is similar to evaluating a double integral. So let's look at the following example. Set up and evaluate the integral of this function over the solid box E, given by x is between 0 and 1, y is between 0 and 3, and z is between -4 and 2. So let's draw the region. Okay, so this is x, this is y, this is z. X is between 0 and 1. Y is between 0 and 3, right? And then Z is between 2 and -4. Okay, so we have a rectangular box, looks like that. Can you imagine, everybody? Okay, so this is the rectangular box. Let's have the integral. So similar as the double integral, do you remember for double integral, if our region in the xy plane is a rectangle, and then the order of integration does not matter. And here, because it's a rectangular box in the space, so the order doesn't matter. Okay, so rectangular box. So order does not matter. Okay, doesn't matter. Okay, so just up to you. We can do x first. So x goes from 0 to 1, and then y goes from 0 to 3. Z goes from -4 to 2. Okay, e to the x, well, this is cube root of y, so y to the 1/3, z squared, and then when you close it, don't forget we have pair. So this guy is dz, then we have dy, dx is outside. So far so good, everybody. Okay, so we calculate from the inside to the outside. So let's copy down those. And integral with respect to z, we copy down this. Z cubed over 3, right? Evaluate from -4 to 2. dy dx. And then what happened? So this is 0 to 3. We have e to the x, y to the 1/3. We plug in -4. We plug in 2 first. 2 cubed is 8, so 8 over 3 minus. We plug in 4. Well, negative can become plus. 4 cubed is 64 over 3. And then we have, let's see, we still have dy dx. Well, this is the same as 72 over 3. 72 over 3 is the same as, let's see. So 72 is like 9 times 8. 9 divided by 3 is 3. 3 times 8 is 24. So far so good, everybody. Okay, so we can pull out the 24, and then we can integrate the y. So e to the x stay there, y to the 4 over 3 over 4 times 3, evaluate from 0 to 3 dx. And then let's see, we plug in 3 first. Oh, so this is 3 times 3 to the 4 over 3. That's the same as 3 times 3 to the 1 over 3. Okay, and then over 4. Subtract 0. 0 is gone. So far, so good, everybody. Okay. We can also move out this guy. Well, when we move out this guy, 4 and 24 cancel, we have 6. 6 times 9 is 54. 54 and 3 to the 1/3. And then integral of e to the x is e to the x. Evaluate from 0 to 1. So we plug in 1 first. E to the 1 is e. Minus, we plug in 0. E to the 0 is 1. So far, so good. So this is our answer. Okay. So there's no way you can simplify it. So don't multiply the 54 and 3, okay? This is cube roots of 3. We cannot multiply them together. Okay, so the integral we just computed is often write triple integral on the solid E, okay? F of x, y, z, dv. So v is the volume differential. Okay. So last time when we talked about double integral, we use R to stand for the region in the xy plane, and we use area differential. But now when we're looking at triple integral, we use E to denote the solid box, okay, the solid in the space, and we use volume differential. Okay. So the mass density mu of a material at a point xyz inside a solid is defined as follows. We take a small portion of the solid containing the point xyz. Suppose this portion has mass change of m and volume change of v. The density at the point is approximately by change of mass over change of the volume. To get a precise measurement of the density at the point, we take the limit as the portion shrinks to the point. Okay, so this is mu. Mu is the density function. Important interpretation of the triple integrals. Let E be a three-dimensional solid region in space. Let mu represent the mass density of material used to fill the solid region E. Then the triple integral of mu computes the mass of the solid E. Okay? If the density is always 1 throughout the solids, then the triple integral just gives us the volume of the solid. Okay? So I want to remind you, so this guy, single integral gives us area under the curve, right? And then double integral. Oh, sorry. This is f of xy. This gives us volume. Okay, so volume under a surface. So this is the surface. It gives us the volume under the surface. And then the triple integral x, y, z, we have the volume differential, give us the mass of the solid. So far, so good, everybody? So keep those in mind. Why? Suppose we partition the solid E into small pieces, each with volume change of V equals change of X times change of Y times change of Z, and the mass change of M. Know that change of M is approximately by the density function times change of V. So if the density function is sampled at a point somewhere inside the pieces, the total mass is the sum of the change of the mass. That equals the sum of mu change of V. That is sum of mu change of X, change of Y, change of Z. Now, when we take the increase the number of little pieces and let each size goes to 0, then this guy becomes the triple integral. Mu is the function and the volume differential becomes dx, dy, dz. So far so good, everybody? Okay, so let's do some examples. So triple integrals over more general 3D region. Example, let f be x squared. Let E be the solid in the first octant. So in space, instead of quadrant, we have octant. Bounded by 3x plus 2y plus z equals 6. Set up, but don't evaluate the integral, the triple integral. Okay. So how do we solve this kind of problem? So first, let me draw a picture here. Okay. So let me ask you, what's the total possibility of the order could be? So here we have 3 boxes. We want to fill with dx, dy, dz, right? The first box, how many choices are there? 3. So it could be any one of the dx, dy, dz. Well, then after we pick one, there's only 2 choices left. And then after we pick 2, there's only 1 choice left. So there are total 6 possible orders. So all the 6 possible orders are dx, dy, dz, dx, dz, dy, dy, dx, dz, dy, dz, dx, dz, dx, dy, dz, dy, dx. Okay, 6 possible ways. Yeah, so more complicated than the double integral. Double integral, we only have 2 possibilities, dx, dy, or dy, dx. But here we have 6 possibilities. Okay, so how do we do it? First, what is this solid? Okay, so this is a plane, right? We know 3 points can intersect a plane, right? Usually we can find the 3 points across the coordinates axis. So let's say on the x-axis, it means y and z are 0. If y and z are 0, then we have 3x equals 6, x equals 2. So at this point, okay, how about on the y-axis? Well, and then x and z are 0, so 2y equals 6, y equals 3. Okay, how about on the z-axis? So x and y is 0. Oh, we get z equals 6. Let's say this is 6. Then, what do we have? We have a plane. Oops. Okay. Can you imagine this is the plane? Okay. So far, so good, everybody. So this is a plane. And E is the solid in the first octant bounded by this plane. So which is under this plane. Okay, under this triangle. So we want to set up the triple integrals in the following orders. dz, dy, dx. Okay, let me teach you how we think. So, you know, we have x squared inside, and then we have dz, dy, dx. So you look from the outside. Okay, the first set, look from the outside. Okay, the outside is dx. Then, you know, where is dx? Dx means it's a little width on the x-axis. So this is dx. So look at the outside. Because it's dx, so we draw dx on the x-axis. Okay. Second, that is dy. dy means we're gonna draw our small rectangle on the xy plane. Okay, because the first step we get dx, second step we have dy. Then we draw this little rectangle on the xy plane. What's that mean? So you draw the plane that is perpendicular to the z-axis. Okay, and this is the rectangle. Okay, so this is the rectangle, and then z is just we get this guy. Okay, this is the cross section. Okay, so now let's see. Let me use a different color. I want to indicate. So the second step, we draw this rectangle, right? So first, let's look at the x. The x goes from 0 to 1, right? So x goes from 0 to 1, and then we know y. So y is a function of x. Okay, so express y in terms of x. So y is function of x. Okay, so let's see here. So let's look at this green rectangle, and the lower value we have y equals 0. The upper value is on this line. What is this line? This line is when the z is 0. So it's on the plane, but z is 0. Okay, so it's on the plane. Our plane 3x plus 2y plus z equals 6, and the z is 0. Okay, so that's why we get 3x plus 2y equals 6, and we want to solve for y, right? We want to express what's the y boundaries. Okay, so y equals 6 minus 3x divided by 2, so 3 minus 3 over 2x. So y goes from, so this is x, my y goes from y is 0, okay, and then go until this line. This line is 3 minus 3 over 2x. Okay, so far so good, everybody? Okay, so after we draw the y, and then we have to figure out the z. So here, let me use a different color. So what is the z then? Okay, so given any point, I mean general points, don't pick the end point because it's not a general point. Pick a general point, okay, on inside this rectangle. What is the region here? Okay, what's this region here? The lowest value is z equals 0. What is the highest value? Well, highest value, the z is on the plane, right? So step 3, z is a function of x and y. Okay, and on this plane, what is this plane? This plane is 3x plus 2y plus z equal to 6. Solve for z. So z is 6 minus 3x minus 2y. Okay, so this is the top bound. Z goes from 0 to 6 minus 3x minus 2y. So this is how we set up the triple integrals. First, draw the region, and then look from the outside to the inside. Okay? Yeah, we will do a lot of examples here. So why don't you pause the video and then try to work on part B, and then after you're done, we can go over together. Are you done? Yes? Okay. So let's do it here. So we want to find the z, the x, the y. Okay, so let's first draw it. Okay, we know this is 1, this is 3, and this is 6. Oh, sorry. I just realized x is x is 2, it's not 1. So just need to change one thing here. Sorry. This is 2. So x goes from 0 to 2. And then everything else stay the same. Okay. Just change back. Okay. Let me make this graph better. Okay. So with this. So 1, 2. Yeah, so that's why sometimes it's better to put the scale there. Otherwise, we don't know. We forget 1, 2, 3, 4, 5, 6. We forget what is that number. So, and here. Okay. So now we want to set up our integral like this. And then we have dz, dx, dy. Okay, what is the outside? Outside is dy. Well, then we look at the y-axis. What's the dy? dy is right here. Okay, and then what's the second one? Second one is dx, which means I draw my rectangle on the xy plane. So xy plane, look at this width. Make a rectangle perpendicular to the y-axis. Okay, so this is a rectangle. And we can set up y goes from 0 to 3. And then the x. So this guy, x is 0. This guy, see? This guy is on the line. Okay, the line on the xy plane, and it's the same line as the previous step, right? So we have 3x plus 2y equals 6. But in this case, we want to solve for x in terms of y. Okay, so x in terms of y, then how do we get it? X equals 6 minus 2y over 3. So 2 minus 2 over 3y. Okay, so x goes from 0 to 2 minus 2 over 3y. Okay, and then the third step, draw a point. Okay, so draw a point on the rectangle. Okay, and then imagine how would the point go? So the point goes from the xy plane, increase up to the plane, right? So the bottom, let me right here. So draw a point on the rectangle. Okay. So here we get the bottom, z is 0, the top still z in terms of xy, so the z in terms of xy, so we still have z equals 6 minus 3x minus 2y. Is that okay, everybody? So we still have the same z here. Okay, sorry, too many arrows. So z goes from 0, 6 minus 3x minus 2y. So this is how we set it up. So far, so good, everybody? Yeah, sorry about too many arrows because I really want to point out to you how we think. Probably the next example, I don't write so many circles or arrows there. Then the solution will be more clear or neat. Okay, all right. Do you have the same answer? Okay, so here we just do setup. We don't evaluate. Let's continue. So let's see here. So let's draw again. 1, 2, 1, 2, 3. 1, 2, 3, 4, 5, 6. sometimes it's good to have a big picture. Okay, so x, y, z. All right, and the function in the middle is the same. So here we still have x squared and dx, dz, dy. First, we look at the outside, right? We look from the outside to the inside. So dy, so where is dy? Oh, here, right? dy is here. Then dz, see? dz, which means we want to draw a rectangle on the yz plane. Where's the yz plane? You go up, right? So this is the rectangle. Okay, so my y goes from 0 to 3. And then let's look at this rectangle. The bottom z equal to 0. The top, okay, so this is a line. This is a line on the yz plane, which is our plane intersects the yz plane. Yz plane means x is 0. Okay, if x is 0, we have 2y plus z equals 6. Okay, so 2y plus z equals 6, and we want to express z in terms of y, so z equals 6 minus 2y. Okay, so z goes from 0 to 6 minus 2y. So far, so good, everybody. Then last step, pick a point. Okay, pick a point on the rectangle, and then now we'll go toward the z direction. So it's from here to here, somewhere on the plane, right? So this guy corresponds to x is 0, and this guy is on the plane, but you want to solve for x in terms of y and z. What is the plane again? The plane is 3x plus 2y plus z equals 6. So x equals 6 minus 2y minus z over 3, right? Which is 2 minus 2 over 3y minus z over 3. So far, so good, everybody. Okay, so let me write it down. This x is from 0 to 2 minus 2 over 3y minus z over 3. So far, so good, everybody. Yeah, so look from the outside to the inside. So when we set it up, we look from the outside to the inside. But when we evaluate from the inside to the outside. Yes. So I know this session is not easy. Please do lots of examples, okay? Please do tons of examples. And then we can learn from the examples. Okay, so last one. We know there are total 6, okay? Here in class, we only do 4 of them. But I really hope that after class, you can try the other remaining 2 order. Then you have all 6 order complete. Okay, so we have 2, 3, 6. Okay, so set it up. So first, look from the outside to the inside. dz, where is dz? On the z-axis. So this is dz. Then dx. So it's on the x z plane, right? So xz plane. The rectangle is on the xz plane. So this is our rectangle. So far, so good, everybody. Okay, so z goes from 0 to 6. How about x? We want to express x in terms of z. So this guy is x is 0. But this guy, This is the line, right? The line on the xz plane. Xz plane means the y is 0. So find our plane and we let y be 0. We get 3x plus z is 6. 3x plus z is 6. So let me ask you again. We want to solve for z in terms of x, or we want to solve for x in terms of z? Okay, x in terms of z, right? So x equals 6 minus z over 3, 2 minus z over 3. So x goes from 0 to 2 minus z over 3. Okay, what's next? Pick any point on the rectangle and imagine when we're going to the y direction. So we go to the y direction. Here is where it intersects the plane. So let's see. Here, this is y equal to 0, but on the plane, we want to solve for y. So right, the plane is 3x plus 2y plus z equals 6. Solve for y in terms of x and z. We get 6 minus 3x minus z divided by 2. That's 3 minus 3 half x minus z over 2. Okay, so y goes from 0 to 3 minus 3 over 2x minus z over 2. So far, so good, everybody. Actually, you can also evaluate these integrals, okay? And then you will realize all of them equals the same thing. Do you want to evaluate one of them? So it might have some work. Let's see here, because you might need to end up with something complete square or some quantity to the power of 3. Then you have to multiply out. It takes some time. Okay, so I will leave it as an exercise. Or if you really want to work on it with me, feel free to talk to me after class. I'm happy to let's investigate together. Okay, let's continue. Example. Consider the solid E that lies in the first octant and is bounded by the cylinder x squared plus y squared equals 25 and the plane x plus z equals 5. Set up, but don't evaluate, a triple integral that computes the volume of E in the order of dz, dx, dy. Okay, let's see. Let's draw the picture first. So we have here, so x, y, z, and then we have the cylinder x squared plus y squared equals 25. So the radius is 5. So we draw let me draw a better circle there. Okay, this is a better circle. Let's say this is 5. Okay, a cylinder means it just go up. Okay, and the plane y plus z equals 5. What is that? Well, this is on the yz plane, right? On the yz plane, and when you see when they cross the y-axis and x and z-axis, when y is 0, we get z equals 5. So 2 points can fix the line, right? So 5 is right here, and then when z is 0, we get y equals 5. So it also passes through this point. Let me see. Let me make it better. It looks like 5 is right here. Okay, so the line passing through those 2 points. Okay, so now what happened? It will intersect the cylinder, and what do we get? Can you imagine? We should get something like that. Can you imagine, everybody? We should get something like that. Okay, so we want to, the solid E is in the first octant. Okay, so that's why in order to look at the first octant, we need to restrict. Okay, so first octant is this guy. Can you imagine, everybody? Okay, so this is in the first octant. And then, we want to set a triple integral that computes the volume. Okay, now let's see. Let me use a different color. So volume equals this region E1 dV, but V we choose the order dz, dx, dy. Okay. dz, dx, dy. Now let's see. We look from the outside to the inside. dy, where is dy? Here, this is dy. Okay. And then we have dx. So this rectangle is on the xy plane. Okay, here. This is the rectangle. Now let's see. Y goes from 0 to 5. And then how about our x? Well, here, x is 0. Here, this is on the circle of the xy plane, and you want to solve for x in terms of y. So x equals 25 minus y squared. Is that okay, everybody? Because it's in the first quadrant in the xy plane. So it's the square root. Okay, if it's in the bottom, then it's going to be negative square root of 25 minus y squared. Okay, so here x is from 0 to square root of 25 minus y squared. But now how about the z? So pick any point on this rectangle and then go to the z direction. Okay, until it touch the plane. You see? At the bottom, z equal to 0. But at the top is at the plane. At the plane is y plus z equals 5. But we want to solve for z, so z is 5 minus y. So z goes from 0 to 5 minus y. So this is how we set up the triple integral. Is that okay, everybody? Do you have the same answer? Okay, good. Let's continue. Alright. Let's see. Next example, find the volume of the region D bounded by the paraboloids. Okay, so we have two paraboloids. Let's see. Okay, so first paraboloid, y equals x squared plus z squared. Wow. So that looks like this. Right? And then y equals 16 minus 3x squared minus z squared. So it's like 16 here. And then we have a paraboloid going, going like that, right? They kind of intersect, and they should intersect at an ellipse, okay, or circle. Let's see. So how do we find that intersection? Well, this intersection, let's see. We solve the system of equation y equals x squared plus z squared, y equals 16 minus 3x squared minus z squared. So we set it equal x squared plus z squared equals 16 minus 3x squared minus z squared. Okay, so now let's move everything on the left. For x squared 2z squared equals 16. We want to see, because the coefficient of x and z are different, we're gonna get ellipse. So the standard form for ellipse, we make the right hand side is 1. So with both sides divided by 16, we have x squared over 4, and this is over 8 equals 1. Okay, so what does that mean? Well, that means if you're gonna project this region on the xy plane, we will get an ellipse where the major axis is on the z, right? That is square root of 8. Square root of 8, let's say this is square root of 8. And the minor axis is on the x-axis, which is 2. Okay, so you see, we get an ellipse. Okay, so this is like the projection of that region on the xz plane. And we gotta do that, okay? So now let's continue. So let's set up. So volume. Then we should put 1 in the middle. And okay, here, which order is better? I would say they're kind of similar difficulties. So let's do dy, because you can see our problem, y is a function of x and z, so it's better to do dy inside. So that means y is a function of x and z, so it's easier. And then we can do dz dx. Let's do dz dx. Okay, let's choose this order. So if I don't have a requirement in the problem ask you to use this order, then you can use any one of the 6 order. Okay, which anyone as you want. So okay, let's see. Dx, where is dx? So dx is on the x-axis, right? So this is dx. Okay, and then you think about, okay, the next one we have dz. Z is, so you want to draw a rectangle on the xz plane. This is the rectangle. So x goes from 0 to 2, and then z goes from, so the bottom, z is 0. The top is on the ellipse, which means we want to solve for z in terms of x. So let's look at this guy. We solve for z. Then z squared is 16 minus 4x squared over 2. So z is the square root of 8 minus 2x squared. So from 0 to square root of 8 minus 2x squared. Okay. And then how about the y? Okay, so pick any point on the rectangle. Then we're gonna go to the y direction. So go to direction. Where is our solids? Our solids, you can see with the smaller paraboloid is here. The upper paraboloid is here. Can you imagine? We have 2 paraboloid. Okay, so this picture is this example is interesting because now you can see the y doesn't start with 0. It's actually this piece, this paraboloid. Okay, so the bottom paraboloid is y equals x squared plus z squared. So x squared plus z squared. The top paraboloid is the 16 minus 3x squared minus z squared. So this is how we set it up. So far, so good, everybody? Okay. This problem also it is hard to compute the integral, so we don't need to evaluate. But the next example I will evaluate with you. Okay, yeah. Usually the triple integrals it could get more complicated, and then the integral is harder to solve. It's harder to solve, but for this example, it's harder to solve, but we are still able to solve it. It just needs some trig integrals, and then trig identities, and then some algebra, use substitution, play with it around, and then we're able to solve it. It's just more complicated. Okay, but I really want to, maybe I can set it up with the other order. Okay, I can do it with you. So let's practice. Okay, because I would say the most difficulty is how to set up the triple integral. Once you set it up, then just compute from the inside to the outside. Okay, and let's see. So, or we can use the other order. We can use, it's better to have dy, y in terms of x and y. So dy, let's keep it inside. And now let's do dx, dz. Okay, so in this case, what happened? Well, we're gonna have the picture again. So we have this guy, this guy, this guy, and then we project here, right? This is square root of a, this is 2. Okay, so now dz. So dz is right here. Okay, then next one is dx. So we want to draw a rectangle on the xz plane. So this is the rectangle, right? And we want to express x in terms of z. So this guy, x is 0. This guy, we want to express x in terms of z. So let's find that ellipse. Here, this is the one, right? So solve for x. X is 16 minus 2z squared divided by 4. And then take square roots, right? So square root of 4 minus z squared over 2. Oh, my z and 2 look similar. 2. Okay? So z is from 0 to square root of 8. X is from 0 to square root of 4 minus z squared over 2. Finally, the y also, so we pick a point on this rectangle and then go to the y direction. So it cross the solids at the lower paraboloid and the upper paraboloid. Okay? So what is this pieces? The lower paraboloid, y equals x squared plus z squared. The upper paraboloid, y equals 16 minus 3x squared minus z squared. So x squared plus z squared to 16 minus 3x squared minus z squared. Whew. Okay, everybody? Yeah, so this is how we set up using the other order. Okay. Alright, let's continue. So the previous examples, we are given the information, the surface, and we draw the picture, and then we set up the triple integral. Let's look at this example. We actually are given the triple integral, but what we need to change the order, okay? Which means based on the information of this triple integral, we need to draw the solid. And then, based on the solid, we can change the order of integration. So let's draw it. We have x, y, z. Okay, so from the outside to inside, z is from 0 to 4 roots of pi. Let's say this is 4 root of pi. And then y is from 0. So this is z. Y is from 0. Where's y equals 0? Y equals 0 is here. Okay? To y equals z. So y equals z on the yz plane. What is that? Is something like that, the line, right? So far so good, everybody. So z is from 0 to 4 roots of pi, and y is from 0 to this. So imagine this is like our small rectangle, right? This is the dz, and then y is from 0 to this line, y equals z on the xy plane, yz plane. Okay, now how about x? X is x. So any points here, we start with x equals y. Where is x equals y? So let's say x equals y is right here. And so imagine this guy, if we gonna project here, we will actually get something like that. Okay, here. Okay, so this line is x equals y. Okay, so let's see here. Probably here. So okay, this. So if we go to the x direction, this is the line x equals y, and x equals z. Well, this guy is x equals z. So we have this guy is x equals z. So what is the region then? Well, let me draw it. So the region is this piece. Okay, so on this rectangle, my x is from x equals y to x equals z. Okay, so we get these pieces, and then the solid is this guy. This is our solid. So far so good, everybody. Now we change the order. Okay, so let me draw a simple picture here and see how we change the. Okay, so let's see, like that, and okay. All right, so now we change the order. So f is still the same function. Actually, this example, we have to change the order, then we're able to solve. Because with the original order, we're not able to solve. Look at the first one. We need to integrate sine x to the 4th dx. No, not able to. Okay? If we have like x cubed sine x to the 4th, yes, we can use u sub. But just this guy, we're not able to solve this integral. So this is similar to last time when we talked about the double integral. With some order, we're not able to solve, and with some order, we're able to solve. Okay? All right. Let's see here. So z. Oh, we still have z. So we still have the dz here. Okay, dz here. And then x. Oh, so now dz is here, x. So we are, this is our rectangle. Okay, the x is from 0 to, what is this line? This line is x equals z. Okay, so z goes from 0 to 4 root of pi, and x goes from 0 to z. And now how about y? Well, actually in this problem, if we use this order, y is easier because we're talking about this region. Then y is from this guy to this guy. So this guy corresponds to y equals 0. This guy corresponds to what is that line? What is this line? This line is y equals x. See? It's the line y equals x. So y is from 0 to let's see. Yeah. So from 0 to x. So far so good, everybody. Okay, let's continue. Let's start to solve it. So first thing, integrate with respect to y. So 0, 4 root of pi, 0 to z. Okay, so y squared, so it become y cubed over 3. 12 over 3 is 4. So 4y cubed, z cubed, sine x to the 4th. So, and then y from 0 to x, dx dz. Okay, now we plug in x. So we have 4. So we plug in y is x. So we have 4x cubed, z cubed, sine x to the 4th. When we plug in y is 0, we get 0. That's nice. Okay, do you see the magic? Because of the x cubed, we're able to integrate sine x to the 4th. Just use u substitution. Let u be x to the 4th. du is 4x cubed dx. Awesome. So we have this is u of 0, u of z. 4x cubed dx become du, and then we have z cubed is like a constant, and we have sine of u. Well, what is sine of u? Integral of sine u is plus or minus cosine. The derivative of cosine is minus sine, so the integral of sine is minus cosine u, and then times z cubed. The u evaluate, what's u of 0? Well, that's 0 to the 4th is 0. The u of z is like z to the 4th dz. So far so good, everybody? Okay, so we have 4 root. Oh! My 4 root looks like 4 times square root of pi. Let me move the 4 smaller. Okay. Make the 4 smaller. Okay. And this 4 is also make it smaller. Okay, now we plug in u equals z to the 4th. Cosine z to the 4th. This guy is inside the cosine. The z cubed is outside. When we plug in 0, oh, minus become plus. Cosine 0 is 1. Then we still have z cubed. So far so good, everybody? Oh, now let's integrate it. See, this guy, we can use u substitution again, right? So let u be z to the 4th, du will be 4z to the 4th d. First of all, it's better to separate them. Okay, so let me see. Yeah, good. So first I want to separate them because for the z cubed dz, we don't want to do u substitution for that one. So let's separate them. Okay, so for the first integral, we do u substitution. And then, oops, this is z cubed. So z cubed dz equals 1 over 4 du. Then that guy is cosine u 1 over 4 du. u of 0, u of forward of pi, plus integral of z cubed is z to the 4 over 4, evaluate from 0 to 4 root of pi. Okay, so integral of cosine is sine u, then u of 0, 0 to the 4 is 0, u of 4 root of pi, 4 over pi to the power 4 is pi. Okay, and then 4 root of pi to the 4th is pi. Over 4, when we plug in 0, is 0. Now let's see. Do you know what is sine pi? So sine looks like this. Sine pi is actually 0, and sine 0 is actually 0. So that crazy term is 0. You might say, what? And that is possible. But think about it. That is because our z value is from 0 to 4 root of pi. If I give you the z value is from 0 to 4 root of pi over 2, then you will get a non-zero answer for it. Okay, so you cannot say, oh, it's 0. Why do we need to do those work? We need to do those work because we need to get the function in u. Then we can plug in any number. We're not only plugging in the 4 root of pi, right? We can plug in other numbers. Okay, so we need to learn this techniques, methods. Okay, finally, so the answer is pi over 4. Okay, so now in this example, we have learned maybe in some order we're not able to solve the triple integral, then we need to change the order. But how do we change the order? First, well, we think reversely, right? Previously, we are giving the surface, the boundaries, and we want to set the triple integrals. Now, based on the triple integrals, we can figure out, okay, what is the z bounds, what is the y bounds, what is the x bounds. Okay, and then based on those information, we can draw the this solid. Okay, then we can use the other order to set up a new triple integral. You can see that the new triple integral, the boundaries are different. Okay, so we cannot use the same boundary and just replace the order as a different order. No, not that easy. Okay, so I would say triple integral is one of the hardest sessions in Calculus 3. So I really hope that you can spend more time on this session, look through the class notes, and then do your homework, check your solution carefully. And if you have more time, please do more exercise from your textbook and then ask me. Okay, I'm very happy to help you. Alright, let's continue in video part B. Okay, so video part B, we'll talk about, so what we're doing right now, we're doing triple integrals in Cartesian coordinates. So next video, I would introduce the spherical coordinates and cylindrical coordinates. Okay, see you soon. Bye.